We've had a few questions about number 5 on assignment 9 on WebAssign, and it's based on number 14 on page 306. So this is the problem I want to take a look at. We're asked to find the absolute maximum value and absolute minimum value, if any, of each function. So the first thing, especially when you're getting used to these functions and how they behave, the first thing you're going to want to do is take a look at the graph. So on the next slide, I'm going to go ahead and show you the graph of this function. I graphed this thing using the Desmos graphing calculator, and you can see it looks like we're going to have some maximum and minimum values. Over here at what I believe is 1, 0.5, we're going to have a maximum, and it looks like it's an absolute maximum depending on what happens over here. And looks like right here we're going to have a minimum, and it looks like it's going to be an absolute minimum depending on what happens over here. So what we'll do is we'll go ahead and do our analysis of this function with our first derivative and our second derivative, and then we'll see what we can find out. So when we're trying to optimize functions, the first thing we need to do is go ahead and take that first derivative. We're going to have to use the quotient rule on this function. It's a rational function. My numerator is x, and you know we usually make u equal x, and that means that the derivative, which typically some people call it du over dx, I'm going to call it u prime just for notation's sake. U prime then is just 1, and then our v is the denominator, which is going to be 1 plus x squared, and our v prime is 2x. So when we do the first derivative, we do vu prime, so that's 1 plus x squared times 1, which is still 1 plus x squared, minus uv prime, which is x times 2x, so that's 2x squared, divided by v squared, which is the 1 plus x squared, and the whole thing's going to be squared. And we can simplify that a little bit. You can see on top we end up with 1 minus x squared over 1 plus x squared squared. And then what we need to find is some critical points. Now, critical points occur at two places where the function, the derivative function, is 0 and where it's undefined. This function will never be undefined because no matter what number we put in here, we're always going to get a positive value. And when you square that, you get another positive value. So we're never going to equal 0 in the denominator. For the numerator, what we do is we take it and we set it equal to 0 to find out when it equals 0. And you can see that gives us x squared equals 1. So our solutions are plus and minus 1. Those are our two critical points. And then depending on whether or not you're performing the first derivative test or the second derivative test, you'll make a sign diagram. I'm going to go ahead and do the first derivative test. I don't even want to mess with making the second derivative of this thing. And I like doing math with positive and negative ones. So here are my three little subintervals when I post my critical points. I'm going to plug a 0 in to the derivative, f prime of 0. And I'll get a 1 on top and a positive 1 on bottom, and so that derivative is positive. So my function's heading this direction, which is what we showed when we saw the graph. When I plug a negative 2 in here, I get a negative 3 on top, and again I get a positive number on bottom, so that's going to be negative. So this thing's negative, which is what we expected from the graph. We do have a minimum here. We're just trying to figure out if it's absolute or not. And then at 1 we do the same process, and as it turns out we're going to get basically the same results. I'm going to get I'm going to plug a 2 in there, not a 1. If I plug a 2 in, which is over here, I get a negative value again, negative 3 over 25. And so that's showing me that this is a max. Now, that's great. We already kind of knew from the graph that we have an absolute min at negative 1 and an absolute max at 1. We can plug those values in to figure out what the y values are. But what we really need to know is, are we certain that these are absolute max and mins? And for that, we're going to need to go back to our friend the limit. What we basically need to show is that this function over here on the far right side isn't going to take off and go below what we think is the minimum right here. And we need to show that over here on the left side that this part of the function isn't going to take off and go above that point that we have there. And like I said, what we're going to do is we're going to use limits to show that. So this is probably a little bit of overkill, but just to show you that this is definitely, these are definitely absolute max and min values, I'm going to run through a quick little demonstration with limits. Basically, algebraically, we can manipulate this expression. If I multiply by a form of 1 on top and bottom, which I'm allowed to do. Oh, I just made a mistake. If we multiply by 1 over x on top and bottom, then we can easily see how this limit is going to end up. On the top, I end up with a 1 in the numerator. I get 1. And then the denominator, when I distribute this 1 over x, I get 1 over x plus x. And so then what we do is we basically plug infinity into each of these things. And when you plug infinity into a 1 over x, that goes to 0. And when you then what it leaves us is another 1 over x, and when you plug infinity in that one, that goes to 0. So this whole thing's heading toward the x-axis. It's heading towards 0. It's going to work the exact same way over here, except it's going to be approaching from the other side. But the math is exactly the same, right? We've got the limit as x approaches negative infinity. I'll do 1 over x here, 1 over x here, 1 plus x squared. And again, when we distribute this, we get 1 over x plus x. We're sending x to negative infinity this time. And when we do that, this guy turns to 0, this guy is going to end up turning to 0, 1 over infinity goes to 0, and so this whole thing also goes to 0. This shows us that our function is going to head towards 0, it's never going to hit 0, and that means that on those graphs, and I'll show you again on the slide, our curve is going to approach the x-axis but never cross it. So here's our graph one last time, and all I'm saying is that we've shown that this thing's going to just inch towards the x-axis as an asymptote, but it's never going to cross it, and the same thing's going to happen here, right? We know it never turns around because there's no critical points. These are the only critical points. Alright, so now let's get back down to business with those. We still need to find the y values. F of 1 is 1 over 1 plus 1 squared, which is 1/2. That's what we thought it was. And f of negative 1 is negative 1 over 1 plus negative 1 squared, which is negative 1/2, which is exactly what we thought it was. 1 comma 1/2 is our max, and negative 1 comma negative 1/2 is our min. These are absolute max and min values. So just to summarize what we did, we took a look at the graph to give us an idea what was going on. We took the first derivative using the quotient rule. We found our critical points by setting the numerator of that derivative equal to 0. We played around with limits just to make sure that those were going to be absolute maxes and mins. And then ultimately we just plugged in the x values to get the y values, to get the absolute max value and absolute min value on the function. Use the same kind of math when you're working on number 5 on the assignment, and you should be in good shape. Good luck.